Have you ever really stopped to wonder how the internet actually works? I mean, it's not magic, right? It's all built on a shared rulebook. And that rulebook is called TCP/IP, and it controls literally every single thing that happens online. So today, we're going to peel back the curtain and break that rulebook down piece by piece. Okay, let's just stop for a second and think about this. Right before you started watching, your device had this super fast, almost instantaneous conversation with a server probably hundreds, maybe even thousands of miles away. We're talking milliseconds. But what was it saying? What language was it speaking to make all this happen? Well, that's exactly what we're about to find out. At the very heart of all this is one critical idea, a protocol. The easiest way to think about it is like this. For us to have a conversation, we both have to agree to speak the same language, right? For computers, a protocol is that shared language. It's the set of rules that make sure data isn't just a chaotic mess of electronic noise. It provides the structure. Think of this as our roadmap for today. This is the TCP/IP model, and it breaks down the incredibly complex process of internet communication into four, much more manageable layers. We're going to start our journey at the bottom, in the internet layer, which is all about one thing: giving every device an address and figuring out how to get data to it. So first things first, and this is non-negotiable. Before any device, your phone, your laptop, your smart TV, can send or receive a single byte of information, it needs a unique address. It's exactly like your house needing a mailing address for the post office to find it. It's just that simple. No address, no communication, game over. So how do our devices get these addresses? Well, you've got two options. Option one, the hard way. You could have a network administrator physically go to every single computer and manually type in an IP address. Can you imagine the nightmare? It's so slow, it's tedious, and one tiny typo could bring the whole network down. Or you could just automate the entire thing. That's the real choice here: manual chaos versus automated order. You see, to a computer, an IP address isn't those neat numbers we're used to seeing. Nope. To a computer, it's this: a long, tangled-up string of ones and zeros, a 32-bit binary number. And yeah, it's just as messy and confusing as it looks. Trying to work with this directly would be an absolute disaster for us humans. So to untangle that binary mess, we do something pretty clever. We break that 32-bit string into four 8-bit chunks, which are called octets. Then we just convert each of those chunks into a simple decimal number. And voila! You get the familiar dotted decimal format we've all seen, like 192.168.0.1. So much easier to read and remember, right? And the hero that automates this whole process for us is DHCP, the Dynamic Host Configuration Protocol. The absolute best way to think of it is as the network's official address assignment office. The second your device joins a network, it basically shouts, "Hey, I'm new here, I need an address." And the DHCP server just hands it everything it needs to get started. It's brilliant. And this is what it actually looks like in the real world. This is basically the control panel for the DHCP server running inside a normal home router. See that part that says IP address pool? That's it. That's the specific range of addresses the router has set aside, ready to lease out to any phone, laptop, or tablet that connects. It's automation in action, right there. Okay, so our device has an address. We're on the network. Awesome. But that's just step one. Now, every single time it wants to send data, it has to make a really important decision. Is this message for another device right here on my local network, or does it need to go out to the huge open internet? And the key to making that decision is something called the subnet mask. It's a special number that works like a filter or a decoder ring. It lets your device look at any IP address and instantly figure out which part is the network ID, kind of like the zip code, and which part is the host ID, the specific house number on the street. All right, let's say your laptop wants to send a document to your printer. It looks at the printer's IP address and uses that subnet mask to check the network ID, the zip code. And hey, they match. So the decision is easy. This is a local delivery. The data packet just stays right there on your home network. But now, what about watching this explainer? Your laptop looks at the server's IP address, it applies the subnet mask, and whoa, hold on, the network IDs do not match. The zip codes are totally different. This message is clearly going out of town. It can't be delivered locally, so it has to be sent to a special address, the default gateway. So what is this default gateway? It's not as complicated as it sounds. It's simply the IP address of your router. That is its most basic, fundamental job. It's the central post office for your entire local network. Any data that's not for a local device gets passed to the gateway, and the gateway forwards it on its journey out to the great big internet. So this system seems pretty solid, right? But there was a giant ticking time bomb at its very core. A 32-bit address system can only have so many unique combinations. And with billions of devices coming online, we were on a collision course with disaster. So how is it possible we didn't just run out of internet? Here's the problem in a single number. The original system, IPv4, has a maximum of about 4.3 billion unique addresses. Now that sounds like a huge number, but with a global population of 8 billion people, many with multiple devices, yeah, you can see the problem. We blew past that limit a long time ago. The solution was honestly a stroke of genius. A really clever workaround called private IP addresses. Basically, the internet's governing bodies set aside specific ranges of IP addresses that anyone, anywhere in the world, could use on their private network. It's exactly like how every company can have someone at phone extension 101. It doesn't cause a conflict because it's only used internal. And here are those special private ranges. Now, big corporations, they often use that 10-dot range you see at the top. But look at that last one, 192, 168, something, something. Does that look familiar? It absolutely should. That's the default range used by almost every single home router on the planet. But wait a minute. If these addresses are all private, how do they talk to the public internet? Ah, that's where the next magic trick comes in. It's a service on your router called NAT, or Network Address Translation. It's like a corporate mailroom that lets all of your devices with their private little addresses share the one single public IP address that your internet provider gave you. But let's be honest, private addressing and NAT were always just clever patches, kind of like Band-Aids to stop the bleeding. The real, long-term solution was to build a new, bigger, and better system. And that brings us to the next generation, IPv6. So get ready for a jump in scale that is almost impossible to wrap your head around. IPv4's 4.3 billion addresses felt like a lot, but we ran out. IPv6 gives us 340 undecillion addresses. That's a 340 with 36 zeros after it. To put that in perspective, that is enough addresses for every single star in the known universe. We will never run out again. And you know, one of the best things about IPv6 is just how elegant and simple it is. The address is split perfectly in half. The first 64 bits are for the network, the second 64 bits are for the device on that network. That's it. No more complex, confusing subnet masks. It's just clean and efficient by design. Now, I know it definitely looks a bit alien at first. It uses both numbers and letters. That's called hexadecimal, and it's separated by colons. It's longer, for sure, but that length is what gives it its incredible power. It was designed from the ground up for an internet that is orders of magnitude bigger and more complex than anything we have today. So when you think about it, from your device getting an address, to figuring out where to send data, to all the clever workarounds that kept the whole thing from falling apart, this entire system is just governed by a set of rules. Protocols like TCP/IP are the invisible architecture of our digital world, working silently in the background. And it really makes you wonder, doesn't it? What incredible things will the next set of rules make possible?